everyone, thank you so much for clicking onto the video. Today we're going to be looking at mass spectrometry, so here are our learning objectives. We're first going to look at how mass spec can be used to determine the molecular formula of a compound, and by the end we should be able to use precise atomic masses and the precise molecular mass to determine the molecular formula of a compound. Now we're going to talk about mass spectrometry. So when compounds are placed in the mass spectrometer, the molecule can fragment during the process of ionization, and this just means that the compound breaks up. And each peak, apart from the parent ion, will correspond to a fragment ion, and this information can help us with the structure of the compound. So the peak with the highest mass-to-charge ratio will be normally due to the original molecule that hasn't fragmented, and this is called the molecular ion. And as the charge of all the ions is +1, that means that all the mass-to-charge ratios will be equal to the MRs. And so what we say is that the first species formed is called this molecular ion, and we denote this by square brackets and M and a plus for the positive ion. And this signal, the signal for this M with a plus, this ion, gives the MR of the compound. And this is the peak with the greatest MZ value. So looking at this mass spectrum for butane, signal that we have at the greatest MZ value is this one here. And so this one actually corresponds to the MR of the compound. And we can actually check this with butane because butane has the formula C4H10. And so if we use the values from the periodic table of all the ARs and add them up, we get 4 times 12, which is 48, and then add 1 times 10, which is 10, and so we get 58. And so we can see that the last, signal with the highest MZ value is the MR of butane. Now, when we look at high resolution mass spectrometry, what that does is that it gives it to a more accurate degree. So mass spectra often show masses to the nearest whole number only. However, many spectrometers can measure masses to 3 or even 4 decimal places, and this method allows us to work out the molecular formula of the parent ion. It makes use of the fact that isotopes of atoms don't have exactly whole number atomic masses, except for carbon-12, because we've defined it to be 12. And a computer database is used to identify the molecular formulae from the accurate molecular mass. So examples we have are that oxygen, which we know to have an AR of 16 for the periodic table, if we do it more accurately, the AR actually comes out to be 15.99491, and for hydrogen, which we take to be 1, it actually comes out to be 1.007829. So you can see that these high resolution mass spectrometers give much more accurate ARs. So now we're going to look at a quick calculation, and this is one of the kind of exam questions that you would get. So for example, a compound is found to have an accurate relative formula mass of 46.0417. It is thought to be either CH3CH2OH or H2NCH2NH2. Calculate the MR of each compound to 4 decimal places to work out which one it is given these accurate masses of atoms. And so what we do is we simply just add everything up like we normally would. So for CH3CH2OH, we add up 2 12s, so we've got 24 for the carbons, and then we've got 6 hydrogens, so we do 6 times 1.0078, and then we would add on an oxygen, so 15.9949, and this gives us 46.0417. And then for H2NCH2NH2, we would have 2 nitrogens, so that's 2 times 14.0031, and then plus 6 hydrogens, so 6 times 1.0078, and then add on a carbon, so we add on 12, and so the total for this would be 46.0530. And so we can see that the compound that they found was in fact this ethanol. So this is the compound that they found. So now we're going to talk about harder mass spectra. If a compound contains a chlorine or bromine atom, then two molecular ion peaks will occur, an M and an M+2 peak. And this is due to the two naturally occurring isotopes of chlorine and bromine. So we know that chlorine can exist as chlorine 35 or chlorine 37, and bromine can occur as 79 or 81. And so we get different peaks because of the different isotopes. So for example, say we have chloromethane, CH3Cl. It will have signals at M equals 50 and M equals 52. So at MZ equals 52, sorry, and MZ equals 50. And so 50 will be its value when the chlorine is 35, that's the chlorine present in the compound, and the peak at M+2 will be when we have the chlorine 37 present. And the ratio of these heights will be 3 to 1. And this is because the ratio of 35Cl to 37Cl is 3 to 1. So 75% of the time we'll find a 35Cl, and 25% of the time we'll find a 37Cl. And so this is why the ratio of height is 3 to 1 also. And then looking at bromomethane, CH3Br, we have MZ values at 94 and 96. So 94 is when we have bromine 79, and 96 is when we have bromine 81. And the ratios of the heights of M and M+2 will be 1 to 1. And that's because 50% of the time we find 79s, and 50% of the time we find BR 81s. And so the ratio is 1 to 1. Now, if a compound contains two chlorine or bromine atoms, then an M+2 and an M+4 peak will occur. And so if we look at this mass spectrum of 2-chloropropane, if we have a look at all their ARs, so CH3, CH, CH3 and Cl, so we can have Cl35 or Cl37, and first I'm going to add up this bit. So for this bit we get 3 times 12, which is 36, and then we have 7 hydrogens, so we put plus 7, and this equals 43. And so for the 35Cl, we get 43 plus 35, which gives us 78. And so this is the M plus peak. And then we'll have a look at the M+2, so that's when we have 37Cl, and we have 43, but plus 37 this time, and so we get 80. And so this is the M+2 peak here that we can see. So this is the 80, and this is the 37Cl. And here we have the 78, which is the 35Cl. And you can see that the ratio of them is 3 to 1.